So I don't think this is particularly funny. I just bring it up to kind of belabor the point that there can be, even here in the soggy Pacific Northwest much of the time, there can be, competition for water resources. What I'm going to focus on here is some actual observations that have been used to estimate evapotranspiration trends in eastern Washington state over the last couple of decades. One of the points worth making is that I'm part of the climate community, and we've mostly focused on winter conditions, but there's variability in summer that matters. And in particular, while we've heard a lot about the kind of water availability side of things, hear about how climate can relate to, or climate variability to the demand side of the problem. All this is made possible through some measurements that were direct measurements from some 5 weather stations maintained by the Bureau of Reclamation. Here they are in the Columbia Basin of eastern Washington. There's the Oregon-Washington border. And so these 5 spots, the Yakima Valley, very heavily irrigated, agricultural intensive. Most of the rest of these. What I'm really going to focus on is a variable that came up before, potential evapotranspiration rather, or PET. It's not just a leading brand of evaporated milk or something. What it actually refers to is the flux of water vapor from the atmosphere into the atmosphere from both the vegetation and the ground itself, given sufficient soil moisture. And so it's essentially what the actual evapotranspiration is if there is adequate soil moisture. The way it is actually estimated is not direct measurements of moisture, but based on an energy budget. A little bit more about that in a second. So cutting right to the chase, here are the trends in summer mean, June through August, of the potential ET at these 5 eastern Washington sites from the late 80s through 2012. And again, there's kind of chatter back and forth year to year. But I think unmistakably over this 25-year record, there is an upward trend. And the units themselves may not necessarily mean much to you, but they're expressed in inches of water loss per day. Something like, early in the record, it was something like, for the stations as a whole, something like 0.27 inches of water. Toward the end, it's something like 0.3, 0.31. Over the 100 days of summer or so, that is equivalent to an extra demand. And you could think of this in an irrigated region. This is probably how much extra irrigation water has to be supplied of something like 3 to 4 inches. Whether that is meaningful or not from a water supply point of view, I don't really know yet. But it seems like to me this is a fairly impressive change over this 26-year record. So that's because it's gotten hotter, right? Well, no. The summer temperatures haven't done anything over that time period. And, sure, there's year-to-year variability. 93 was a cool summer, and we've had hot ones and so forth. But that's not the cause. I get one equation myself here. If we actually look into what this PET is calculated from, it is based on measurements, but again, it's an energy budget kind of perspective on it. We're not actually measuring the flux of water vapor itself. It turns out that there's a term here called, I didn't come up with these terms, anyway, the heat function part. This is about 75% of it, and it has to do with the combination of the heat fluxes due to the net radiation and the sensible heat flux through the soil. So again, 3/4 of the variability is associated with this. The remaining quarter is how fast that water vapor is kind of swept away by the winds. And so basically, the stronger the winds, the lower the relative humidity, and the higher the net heat fluxes the greater the potential ET will be. And it's like, well, okay, that's pretty obvious. And so when you actually look at what the cause of the increase is, it's gotten sunnier in eastern Washington in summer. Now, I'm the climatologist for the state of Washington, and I just ask for you, I didn't know this until I kind of plotted up this data a few weeks ago, and for heaven's sakes, don't tell anybody that I didn't know this. But this change is really quite a bit, these units Langleys per day, whatever the hell that is. But it's about 10% higher in the recent decade than it was early in the record. And it turns out just recently I've looked at some satellite-based estimates at cloud cover, and the average cloud cover in these years was something like 37%, and in recent years it's more like 32%. So it's at least consistent with that. I don't know if the numbers actually work out exactly right, but it is worth kind of poking into this a little more because solar radiation is not the easiest thing to measure. The instruments kind of degrade with time, get fouled, and just so forth. And so what I did, I actually looked at one of the stations here, and I'm going to look at more, and looked and figured every summer near the solstice there would be a day at solar noon or nearby when it was completely clear, and I could see just how strong could it get, the peak radiation. And if you look at the time series here again from early in the record, it goes back to the late 80s to recent. There are some low years here early in the record, but at least the last 2/3, there's no real trend there. This low amounts of solar radiation actually is consistent with some other things that we know about, and that's something called global dimming that occurred, both due to a greater aerosol load, both due to human impacts and some volcanoes, in particular Pinatubo here, I think was 91, 92 or something, and so that kind of helped keep it down here. And just recently we've kind of cleaned up our act to a certain extent worldwide. And so it has been measured across the U.S., lower clear sky irradiance in this, at least in this period than recently. What does it take to get a really high amount of potential evapotranspiration? You need a really sunny day, and I'm the kind of guy who looks at 500 millibar maps before breakfast. Maybe not everybody here is, and you know, that's to your credit, but what it takes really is a big ridge of high pressure, and it's kind of, no kidding. But what I think is a little more interesting is if instead of looking at this was on the kind of daily time scales, this was looking at the top 30 ET days. If I look on seasonal scales and look at the top 4 summers, the patterns here, this is in 500 millibar height anomalies with the yellow and red or orange colors being higher than normal heights and the blues lower than normal. I see quite a diversity in the kind of patterns that account for these high ET summers. If I look at the lowest ones, again, maybe some of it, to a certain extent, it makes sense that with higher heights aloft that you get that, but there's certainly some diversity in these patterns, and you can see the same thing in the low ET summers where it's lower heights aloft or anomalous transport of moisture from the Great Basin into eastern Washington. And this may be kind of a surprise, but the desert Southwest is a source of moisture east of the Cascades in the summertime. So when I looked at a little bit more of the kind of trying to figure out what is causing these changes in this potential evapotranspiration, finally got it right. Here, this is the time series for the 5 stations as a whole over the 26-year record or whatever. You can see on individual years, it has the variability is kind of related to whether this blue trace is kind of boundary layer humidity. The green trace is this 500 millibar heights aloft, that the more moist it is and the lower the heights, the cloudier it is and the less PET. But certainly there's no real sort of trend in the relative humidity, and the one in the 500 millibar heights is pretty minimal itself. So just in summary, the potential of evapotranspiration during the summer in eastern Washington has increased. And that is significant from a statistical point of view when you do linear trends, Kendall tests, and all that sort of thing. It's well above the variability. So it kind of raises the questions, why has it become sunnier? And there, I just in my kind of early poking around, I don't really see obvious connections. There are some, but it just needs more work about what how strongly the seasonal mean variations in this parameter are related to the kind of seasonal mean aspects of the circulation that we could potentially predict next year, next decade, out to the rest of, the century, let's say. So I'm not saying that this trend is necessarily going to increase, but I think it is kind of interesting that it has changed that much, and that we can have that big difference in this kind of measure of demands on the water. And my dream here, and this is subject to kind of generating some funding to do this, is to try to use, if we can figure out the relationships between these circulation patterns and the seasonal mean ET, we can go in with the climate models and kind of see what they're saying about the kind of patterns that support lesser or more of that. So with that, I'll conclude.